All right, so here we go, lesson 224, a little bit more on buck boost, transformers, single and three-phase connections and applications. I'm going to focus on this video on actually calculating amperage and wattage or volt amps, rather. So those are really going to be the two topics we focus on. I'm going to take, really the textbook gives us two nice examples. I'm going to take those examples and sort of break them down in my own words, strip away sort of some of the extra stuff, but really try to get down to it. I think if you can figure out these things we're going to discuss here in this video, you'll have some success in this chapter. So anyway, think about a buck boost transformer. If we think back, this here is essentially a very simple transformer. These are the two components we're using on a buck boost transformer. We have a primary input, secondary output. Generally, on the sizes we're going to use for our buck boost transformers, we're going to see a 120/240 volt primary combined with a 12/24 or a 16/32 secondary, depending what we want to do and how we want to do it. So this is a simple transformer. We use these same coils in a buck boost transformer, except we connect them in kind of this very unique way where we sort of connect them in this series connection. But I tell you that because you got to keep in mind, if we take a transformer like this, the kVA rating or the VA rating, the volt amps or kilovolt amp rating, is going to be the same for both coils. That's kind of goes back to when we first started talking about transformers. It's going to have a kVA rating, right? It's going to be pretty small on a buck boost transformer. So with that said, both coils have the same VA rating or kVA rating. Keep that in mind when we start doing calculations here. We're going to have the same volt amp rating for this coil as this coil. So we know we have different voltages. So the higher voltage is going to have a lower amperage, same VA rating. Lower voltage is going to need a higher amperage, but we're going to have the same VA rating. So we kind of have that seesaw effect between the volt amps, right? So keep that in mind as we do some calculations. So here we have, in this example, again, it's straight out of the textbook, a 208 volt source is going to need to feed a 9.5 kVA load that is rated for 230 volts. Okay, so we have 208 in, we need to use a buck boost transformer to boost that voltage, right? So in this case, we're going to use a transformer with a 240 volt primary, so this is a 240 volt coil, and a 24 volt secondary, so here's our little 24 volt coil connected this way to boost our voltage. Right. So first thing we need to do is, if we think of these coils as these coils have the same number of wraps as their rated voltage. So it's a 240 volt rated coil here. Let's just say it has 240 wraps, right? Or 240 coils around the core. So if we take 208 volts divided by 240, that tells us that we are applying 0.867 volts per turn across this coil. Okay. Why do we care about that? Well, we know we're going to apply 208 volts to this coil, but how many volts are we actually sending through this coil? We're going to use that same 0.867 volts per turn over here. So we know we have 24 turns, or we're going to imagine 24 turns, 0.867 volts per turn. So this coil, we will have applied 20.8 volts through it. So we have 208 we're applying to this through the source. This one will essentially boost us 20.8 volts. We're going to add those two together to give us our total voltage that we're now going to apply to this load. So we add those together, we get 22.8. Textbook tells you, and I'm going to tell you that's close enough to 230. When we get into buck boost, we're never going to be exact anymore. But so instead of applying 230, we're actually going to apply 228.8. Close enough. So what do we want to do next? Let's go ahead and calculate the amperage that this load should pull at 228.8 volts. So we take our simple Ohm's law, 9,500 volt amps, 9.5 kVA divided by 22.8 volts gives us 41.521 amps. Just some simple Ohm's law there. So we should expect 41.521 amps on these circuit conductors, right? Again, it's one load. There's only one path for current to flow. In spirit, it's a series circuit. In a series circuit, your amperage is equal everywhere, right? So we have the same amperage flowing all through this guy. Now let's look at this. We agree we have 41.521 amps here. Where else can it go but here? So this coil is going to see the full 41.521 amps. So we're going to use that information now to actually calculate the volt amps that are induced on this, just this coil right here, right? So we already said it's 20.8 volts, it's 41.521 amps. We can use Ohm's law, volts times amps equals volt amps. So this coil is going to see 863.637 volt amps, right? Now remember, back to that first slide, this coil is going to see and be rated for the same amount of volt amps. So now we can determine how many amps are across just this coil by taking that volt amps that we just calculated for this coil, it's got to be the same for this one, divide by the 208 volts that we already said we're applying, and this coil will now expect to see 4.152 amps, right? Not coincidentally, if you add the 2 amperages up for this coil and that coil, we should get the same. So there again, 41.521 plus 4.152 equals 45.673. So now our entire circuit conductors are seeing 45.673 amps, right? So let's kind of flip the equation, same exact load, but we're going to change it now to 208 volt load fed from a 240 source, right? So you can see the same components. One thing to note, it's now a 240 primary, a 32 volt secondary rather than the 24 that we had last time. So similar process, we're going to have to kind of take some different thinking here. So we have 240 volts plus 32 volts or turns of the coil. So we're going to add up how many total coils do we have across both of these, because we're applying our voltage across both. Add them up to 272, right? And if we go ahead and take that 240 volts that we apply from our source across the 272 turns, we get 0.882 volts per turn, right? So then let's go ahead and take our 240 times 0.882 volts per turn. That gives us 211.68. So this coil is going to see 211.68, right? So that means if we look at where this load is connected, it's just across this little coil here. So this load is not going to see 211.68 volts. Again, close enough to our 208 that we wanted to see. Just to kind of complete everything, because we're going to need it later, this 32 volt coil times 0.882 volts per turn is going to see 28.224 volts on this little section. We'll need that later on. Okay, so now let's go ahead and take our, let's find out what the amperage is just in this portion of the circuit or going through the load. So we take our same 9500 volt amps. Ohm's law says we can divide by our applied voltage, 211.68. Now it gives us 44.879 amps of current are applied through the load, right? So now let's go ahead and see how many amps we think we should see in this entire coil across here, right? The 240. So we take 9,500 volt amps divided by 240. That now gives us 39.583. So we should expect to see 39.583 through our circuit conductors. Okay. And again, notice we have lower voltage here, higher amperage, higher voltage, lower amperage. You got that seesaw effect once again, right? So now let's kind of break down a little further and see how many amps do we expect in each coil. So at this point, we have already determined amperage, so we're going to take our voltage times our amperage to give us 1,117 volt amps in this coil here. We know we're going to have the same volt amps in the adjoining coil over here. We already established that. So 1,117 volt amps divided by 211 gives us now 5.278 amps in this coil here. So there again, we have sort of figured out all the variables, including amps and volts, and now volt amps for any section here. You're going to need to sort of employ those different tactics when you look at the homework questions, but I think through everything we did here, we've found a way to get to any value in the equation. Now it's just a matter of sort of finding that path. So take a look at the homework. There's not a ton of math homework questions, but I think what we've just talked about will be important in that. So keep that in mind as you go through.